ଆସୁଛି ଦେଖିଲ ଚେକ୍ କଲ ରେଟ୍ ହେଉଛି ତ।
It's pocket इसमें आएगा नहीं. ओह अच्छा अच्छा इसमें आएगा. गिरेगा. अभी ऑन है. Yes, yes. Good morning.
Good morning to all. I will introduce Professor Meenu Ramadas. She is from IIT professor. Now she is working as the associate professor there. And she has done her PhD from the Purudi University, Indiana, USA. And also she has completed MTech from IC Bangalore. And now one of her students, he was awarded the PhD, and three of students are going on. The work is going on, and many students of MTech students, they have completed research work, and she has many publications and also book chapters, and honored with the she honored with the awards, Teaching Excellence Award, Roorkee Water Conclave 2022 Best Paper Award, and AC State of the Art of Civil Engineering Award in 2016, GM Narafe Puraskar 2015, Best Paper presented at the Hydro 2014, and in 2015, Estos H and Basti L. Matun Award for Excellence in Teaching, and many awards we can say. And also, she has four number of projects, sponsor projects in different sponsors, and also she is a membership of Associate Editor AC Journal of Water Resources Planning and Management, Life Member Association of Agro-Meteorological AM, and member of the Civil Engineering Forum CEFI Bhubaneswar, and guest editor special issue of AC Journal of Water Resource Planning and Management, life member of IWWA, Indian Water Works Association, associate member of American Society of Civil Engineering. So she is also expertise in climate and meteorological and agricultural field, and also water resources groundwater. You can explore many knowledge from her. So most welcome.
Thank you. Okay. Am I audible? So the mic is working. Okay. Yeah. So a very warm good morning to all of you. So I see very eager faces. Actually, so this is a very nice opportunity for me also to interact with all of you. You are coming from different institutes across Orissa, and you are coming from diverse backgrounds, and it's a very good thing for me to to be able to be enlightening you with some things that we have done through research and studies over the past few years. So the title of today's session is Estimating High Resolution Soil Moisture Data with the help of remote sensing satellite data sets. So this is a very broad title, because there are a lot of opportunities in the same title that can give you different results. So I have taken one path, but with the same title, you could be using a multiple or different data, or a different satellite, or a different area, study area, and you would be benefiting the users of that, or people who are dependent on services ecosystem of that area. So this is a very broad topic as such. So in this presentation, we will go across the different aspects of this topic, and then finally what kind of a case study we did, some results related to that case study. So none of the results are conclusive. It is, research is still undergoing. So we are in a position to just investigate right now. And I want all of you to take back this to your own institutes and universities and continue, so that you will get more solid results, more confident results. Okay. So currently my student Mr. Akash is working on this topic, that is using remote sensing data, and we are exploring different things. So this application is soil moisture, how to get soil moisture. Another application is we want to monitor the environmental condition. For example, we were looking at the heat wave. We all went through a very serious heat wave condition in the last summer, isn't it? So we can feel it, but how did the land experience it? So we will see that it is affecting the vegetation, it is affecting the soil water content. So can we monitor it to show that the severity of the heat wave was so and so, and we should be prepared for such things? It may happen again next year, or it may be more frequent within the same year. So in that way, how to monitor things using remote sensing, we are looking at. Okay. So a brief outline will be, we will go through introduction, motivation for this research, then what were the very defined objectives and methodology, and some of the findings. We call soil moisture, but it is a perspective. You are looking at soil moisture, soil, but what layer of soil are you looking at? How much depth are you considering? Are you looking at one location only, or are you looking at an extent of area where you can measure many locations and tell that average condition is this much? So there are many questions within that single word. So spatially we have to be very clear what is our extent. Temporally also, are you talking about daytime soil moisture at some point of time in the day, or are you telling average soil moisture throughout the day? So this space, time, all these things matter. So soil moisture as such is a very broad idea. So many people tell about surface soil moisture. That means I am only interested in some 5-7 centimeter or maximum 10 centimeter layer of soil, because I don't have measurement devices to go deeper and measure. So that kind of limitation then comes to us, that our measurements may be restricted to only a few layer, a few centimeter layer, or something like that. So regardless that, we say that soil moisture can be measured. How much water content is there in a particular volume or unit volume of the soil can be measured. Now there are different ways of expressing it. So I can say that in 10 centimeter deep soil, there is 5 centimeter water available. So that is telling you soil moisture in one way. If you take 10, 5. So it is like almost well saturated type of kind of soil. On the other hand, we can also say in 1 meter cube of soil, some percentage is water. So we are looking at volume units. So we call it volumetric moisture content. Another alternative way is mass. That means in this much gram of soil, this much gram of water is present. So we call it gravimetric because it is weight based. So we can express soil moisture itself in a number of ways. And there also we have to be very careful because it may be only an average value we are talking about. Unless we take many samples and tell that this is average, this is the standard deviation, we are not becoming clear to the person whom we are talking to. We are hiding many things and telling soil moisture is 25%. We have to tell soil moisture on an average 25%, but plus or minus 5%. So you are saying some range in which that location's soil moisture can be, isn't it? It is true for any scientific measurement also, isn't it? We have to take several samples, take the average, take the standard deviation and convey it to the somebody that this is the value. Now, when we have soil moisture, it has a maximum and minimum range also, isn't it? So we can fill the soil only up to a particular limit with water. So we have that kind of maximum and minimum limits, and also the lab based measurements that we do, that is gravimetric or volumetric, those are bound to be different from the field values, because in the field we are having an undisturbed soil. When we bring it to lab, we are having a disturbed sample. So there may be some differences that way also. And there is some time delay which may lead to evaporation or moisture content removal, like that. So many things are there which will affect the readings between the lab and the field. Now, when you go to field, obviously we cannot take weight etc. from the field and calculate this thing. So what we generally do is, if we have many like a lot of area to cover with soil moisture readings, we generally use some calibrated instruments, maybe like something like a probe, some sensor based measurement things. So it makes our job easier. We just put it in the ground, insert it into the ground, and the machine will take a reading and tell us volumetric soil moisture content is 38%. So 38% means that idea we get that this is the volumetric moisture content. So accordingly, we can use the same sensor in multiple locations. Within an hour, we can cover more locations, isn't it? Rather than taking sample from there, 28 locations, 30 locations, weighing them, oven drying them, weighing them again. That is how we use this equation for soil moisture measurement, isn't it? So sample mass when it is in the wet or actual condition minus sample mass after it has been oven dried for one day or so, and then to convert it into the volumetric units, we will use the equation. So this equation is easy to apply but tedious for a practical case, because you have to take so many samples, take it to the lab, do the same thing over and over. By that time the error may come. So that way a sensor will remove this much task. You insert the sensor, take the reading, go back. Even the sensors are having storage also. So you can take 10,000 samples, it will still store it in the device. You can go home, insert it into your desktop or laptop, download the data. So things have become easier with the help of these kinds of sensor based devices. Now, these are directly visible to you. We are either measuring the weight or volume or something like that. There are some indirect methods also. For example, there are some sensor measurement that does not measure the moisture directly, but it measures the suction or metric potential. So, metric potential is also related to moisture. Okay. So, if we measure the metric potential, then we can use some retention curves, that is the soil water content on y axis and soil water content on the x axis and the metric potential on the y axis. So, that kind of a curve, you know one value, you go to the curve, find the other value. So, soil moisture retention curves along with these kinds of instruments that measure the tension or the metric potential in the soil can be used to get the water content. So, they are also one alternative. So, these days such instruments are also coming with some kind of handheld reading unit which will convert it and give us. But we can always have more accuracy by knowing the correct retention curve for that soil, go back and find out from there. So, there are many opportunities in that way to find out soil moisture. So, even this field is like undergoing so much research. How can we improve the accuracy of the measurement? Or how can we improve the retention curve? Because every soil in every pocket of the land behaves differently. We can put all of them in one basket like sandy soil, sandy loam, like that, but even their individual properties would vary. So, everyone doing research in soil moisture generally studies the sample extensively to build its own characteristic curves, to understand its soil moisture holding capacity, and then applies that in the research. So, how do we estimate soil moisture? Generally, I have mentioned few methods. Other than that, there are some other measurement techniques also. For example, electrical resistance block. So, this means that when we are using an instrument that can measure the resistance. So, if water is present, definitely that would affect the electrical resistance. So, how much it is affected will tell you how much water is there. So, this instrument would be already calibrated to know that this much water would lead to this much. So, that way it is already calibrated. So, you have a mechanism to read it directly. And neutron moisture meters, those are based on, again, if water is present, then the neutrons released will be stalled, or they will have their speeds would be decreased because of collisions and all with the hydrogen atoms. So, how much that collisions are happening indicates how much water is there. That will be read by the instrument, calibrated, and then give us the reading for corresponding soil moisture. Similarly, gamma ray based, radiation based instruments, that is also like there is a radioactive release of gamma rays. So, what will happen if there is water present? It will be absorbed by these molecules, and therefore, the radiation received by the receiver end would be affected. So, how much water is present would be affecting how much gamma rays are received, or how much low strength they are being received. Then the last two, they are most popular. So, even now when we talk about soil moisture measurement, people assume everything is TDR, FDR, like that, isn't it? So, time domain reflectometry is a very popular traditional way of measuring the soil moisture. So, it measures the time delay which happens due to the presence of water when the electromagnetic energy is released and received. So, if the soil moisture content is high, then the velocity of the received pulse would be lower. So, that way it can correlate with the amount of soil moisture. Then last one is the frequency domain. So, instead of time, that is just referring to the frequency. So, how much water is present would affect the frequency of the received waves, and therefore it can be giving us an estimate of the water content. Now, all these things we generally take it to the field, install or put it in the ground and take the measurement, isn't it? So, our limitations, we cannot cover large area in short time. We cannot have the money and resource to do this experiment daily. Let's say I want daily data or continuous data, more frequent data. So, how do I do that? How do I do this kind of large scale reading data collection on a daily basis or regular basis without spending much time and energy? Okay, so the question remains that how to do that. So, we have a challenging problem there and we need a solution. So, that is where our motivation for this research will come into picture. So, why do we need this data? So, people who are working in agricultural water resources studies would need some idea about how much water is to be supplied to the field from time to time. We don't want to provide too much water. We don't want to affect the growth of the crop also by not providing timely water. So, in agricultural water management, knowledge of soil moisture, how it varies, what is the fluctuation is an important thing. Then, if you are talking about water resources studies, let us say we are trying to uh, have some water balance study. Water balance means we want to know how much uh, runoff is received. And runoff calculation needs to be done after knowing that rainfall gets divided into some recharge, infiltration, evapotranspiration, like that. So, we want to know each component of the water balance clearly, and the major calculation of actual evapotranspiration. It is still a like upcoming research topic, how to calculate actual evapotranspiration accurately. Am I audible to all of you? Okay. So let us continue our session. If you recall, we were discussing about the background. We had some background on the topic, why we should do this kind of research. We discussed that, and then also we reached the point where we have defined very clearly what are the objectives of the research. So for example, in this particular study, my goal is monitoring over a large area so that I can study seasonal changes in soil moisture, or how it is affected by some uh, dry spell, or how some drought monitoring can be carried out later once I have the soil moisture data with me. So we are just bringing out these kind of applications in this particular study. So this was the study area that we focused on. So it is a small watershed in the mid Mahanadi river basin lying in Odisha. So here data was collected from different locations over the spread over this nearly 500 kilometer square watershed area, and it is a typical agricultural watershed. So there are so many fields where we have taken readings from, and this was like a campaign. I mean, every day somebody starts this reading around 7 a.m. in the morning and completes it by the time around 9 o'clock, 10 o'clock. And the same time, some satellite pass was there. That was the background of this data collection. So that was a separate study that was carried out on a separate project and all. But the data was made publicly available. So that data is available for this particular small watershed area. Now, at that time, Sentinel dataset did not have that much popularity. At time where different other satellites were more, Landsat, MODIS, etc. were more popular. So now we have Sentinel, which is easily accessible and which is also making this past year's data available. So we have taken this study area. This is a Rana watershed in near Cuttack. It is located, and here we are using some kind of sensor probes that are used to measure the soil moisture by inserting into the soil. Okay, theta probe, that is the name of the instrument, theta probes. So this is being carried out like a campaign, like I said, on different dates when satellite is passing, data was collected. And here at that time, different satellite was, like I said, used. But now we have Sentinel in our idea. So what we did was, we checked the availability of dates whenever Sentinel was passing over the study area. Okay, Sentinel satellite is our selected choice. And we see that how many dates in the actual data set coincides with Sentinel's pass, Sentinel's dates. So like that we selected some of those or most of the available dates. Now in satellite data there is another hurdle, another difficulty. When there is a lot of cloud cover present over the sky, it becomes difficult for the satellite to get accurate. Yes, yes. So if we want to have the some kind of calibration validation, we should definitely have as much possible number of samples. So the number of samples should not be lower than 50, but the maximum is as much good as you can have. Yeah, and it is also like covering larger area means you better go for more samples. But statistically, it should not be lower than 50, like that. Mm. Yes, Sentinel-2, yeah. Because Sentinel-2 offers like 10 meter, 20 meter, that kind of resolution. Now Sentinel-3 has also come up. So I may change my choice depending on how much I wanted as much variable data over the land as much possible. So instead of going 1 pixel covering kilometer, I wanted in meter, and that too like very good resolution. So that is one motivation for choosing Sentinel. Okay. Mhm. Yes. Huh. So that is purely it is constrained by our resources also. Like I want to cover a larger area, I can choose some rectangular grids, and grid wise I will go ahead and measure. But my grid size may be larger if I don't have enough manpower and time. That constraint will come, and I have to cover the entire thing in one day, so that will be the day's observation over the area. And if my interest is field, agricultural field, then I may have some kind of requirement that it should be like the farmer's field is only this much, I should get maximum points in that area. If the farmer's field is several hectares, then I may go for some larger, you know, uh, intervals. Yeah, but even at that point scale, if I am taking a reading, I have to take few samples from that. One is not enough. That will not be correct. So I may take three and follow a triangulation and get an average for that latitude, longitude, like that. So those are like our resources are also a factor in determining how much we are putting the effort. But scientific standards we have to follow. Like one sample is not enough. I have to take 3, 4 samples and take an average. It is actually affordable nowadays. Only thing is like we have to replace the parts after some. Uh, yeah, it has some wear and tear problem after multiple insertions, and we have to carefully do it. If the soil is too resistant because it is too dry, then the probe cannot go in. Then we have to avoid taking reading. We cannot push it and destroy the sensor thing. Yes, yes. So the soil can be like dry and unable to, manually just put a thing. So we cannot push this sensor down. The probe is a gentle and very sensitive thing. If it goes in automatic, like when you just put it, it's better. So that way, some constraint is always there in these kind of sensors. Yes, patience as well as knowing all these limitations. Like if the soil is too hard, don't push, don't take the risk. Take some other alternative measurement, like that. Mm. Huh. Mm. Yes. Mm. Yes. In groundwater related thing, those are little more advanced because you have to have them some sensing of deep, deep. So like VES is one way, but it is not very a layman cannot come and do like soil moisture. we have to use a particular setup or like establish that thing. Then interpretation is a different task. So the same instrument cannot be used. It is a little more advanced and little more uh, knowledge required for operating survey of groundwater. If we simply wanted to take water level from wells, we can use. We can use sensors that just immerse and then reading. But that is not that is also very okay. But in a ground, if I want to do some sensing of the aquifer or depth of the aquifer, it becomes a little more difficult. Hmm. Hmm. Yes, yes. If our goal is to use satellite based on this experiment, then we have to look at the dates of pass of the satellite over that study area. So if it is passing on in a month, let's say 4 or 5 dates, then on the same day, almost concurrent timing, we should do the experiment, because during the day soil moisture can change completely. So to have more accuracy, whenever satellite is passing, a 3-hour time window or something we can choose and come, because we also have to do multiple points. So it's not possible in 1 hour also. So some, yes, yes. So planning is necessary. When are they passing? What time they are passing? How many people do we have? How many points should we take? Go with the map. Wherever I have to take, the lathlon is already there. I go to that GPS coordinate. I put the sensor, take the reading, write it down or note it down. So planning is very much important here. Rest of the things you can do after going back to the lab. That we have to do after extracting satellite imagery of the same day. It will not be exactly same. That is where we calibrate. We check the performance. We see that there is some error involved. We correct it if necessary. And then use that same equation later on as if it is like good. Like that. If we get more error, then we have to um, either go for a different instrument or different satellite. Why the error is coming? Is it because there were too many cloud correction going on, or is that satellite is not very useful for this purpose? So such things are there. But the choice of everything we make is based on historical evidence. Like somebody used in America with that satellite, or somebody used in India with that satellite. So that kind of some things we are already doing, some research we are already doing to select or shortlist. And then we are finding, okay, in my study area it's not good at all, or in my study area also it is working well. So that way we are minimizing our effort first by looking at the research already done by people. Then we are going to do the so if Sentinel 2A is not good, then I will avoid Sentinel 2A. I will go for the latest one or Modis or some other thing like that. Or maybe a different algorithm has to be applied, not this one, not that one, like that. So some choice we already make based on literature survey. Then we go to the experiment or research part. Mm. Mm. No, we are actually using. Uh, there is a observed soil moisture from our field measurement, right? We are trusting that. We are using satellite also to get some equation or some kind of regression model that will give or that will connect the satellite readings to soil moisture. If that connection is performing good in validation, then that means that regression can be used in any point of time if I have satellite data. So tomorrow I can avoid going and putting the probe. I can trust the satellite data and the regression model to give me the new soil moisture. So there we are developing the model and then using it. So satellite is not directly giving soil moisture yet. We develop the connection and then get the good value of moisture. So every time there is some model development. Maybe sometimes they directly give soil moisture. Even then we have to calibrate, because our local area may not be same as what they intended, or at the time of development of that sensor they thought they will be applying across some part of the country, maybe another country. But now our area is in a different part. What if it doesn't work for that? So we do that model building there. Okay, we'll come to that kind of experiment here. So our goal has been to connect soil moisture with some of these vegetation indices. And vegetation indices are made up of bands. Okay. Then how do we connect? That is by using regression tools. Machine learning based regression is available, or we can have simple linear regression or non-linear regression tools, or we can also have some other totally different type of algorithms that directly connect the bands to soil moisture data. Okay. So in this particular study, we have used some optical range. That means that is the visible to near infrared kind of range to calculate these band indices. And then we have used a regression model that will try to fit the soil moisture data to these predictors. These are some predictors now for us. And finally, we will check, like we have a calibration validation exercise. Following that, we say that this is my model. You can use it to estimate soil moisture. Just collect these bands from the satellite data. That would be our, instruction, that you do like this, you will get some estimate of soil moisture. So we also say this is our error, this is our accuracy involved. So what are these bands and what are these combinations that we were discussing? So the first one is NDVI, that is normalized difference vegetation index. You must have heard of it in different contexts. NDVI values may be higher, suggesting greenness of vegetation. NDVI values can also be negative, that means barren area, rocky area, no vegetation. And sometimes vegetation, if it is in a poor condition, some range is dedicated to identifying that type of thing. So this is also based a relative assumption that something is more green than before. Then it indicates some deficit of water or some poor health of the crop, like that. So the sentinel bands B4 and B8 were identified as red and near infrared. So in each satellite they will have a different naming. I will name band 2 for this nanometer wavelength, but another satellite person can name in a different way, and they will provide a table. Okay, this band means this thing. So don't confuse with number, but that wavelength is important. Which wavelength you want to pick, that is red, then you go for B4, because in sentinel red is B4, like that. So red and near infrared with a 10-meter resolution were available from sentinel. So I can use that equation. NDVI is NIR minus red by NIR plus red. So these are all reflectance values. When I say a band of that pixel has a number, that is a reflectance number. So ultimately some numbers are being substituted there and you get a value of NDVI. Okay. So for a 20 meter size pixels, data may be available, or in this case 10 meter pixels, these band numbers are available. So each pixel on a particular day has a number for red, has a number for infrared, has a number for near infrared, and I will take those and substitute to get the corresponding NDVI of that pixel, like that. On another day, if I take an imagery, another number will come because the things have changed from another day. Or another location, reflectance values are different, numbers are different. So another NDVI value for the same day, another pixel, like that. Now another index is normalized difference moisture index. So NDMI. So you see between NDVI and NDMI, the combinations look similar, but the bands that are being used are different, isn't it? Numerator has something plus, denominator has something minus, but what is being added and what are being subtracted have changed. So that is because they realize that these are the bands that can suggest greenness better, whereas these are the bands that are more sensitive to the moisture present on a landmass. So accordingly, NIR and SWIR that were chosen as these bands. So it's a relative thing, relative to one another, how they are, being sensed will tell us how much vegetation is there or how much moisture is there, like that. So NIR minus short wave infrared by NIR plus short wave infrared can give us a index like NDMI. So these are already established in literature. These indices have already been developed by scientists. They already checked whether it is actually capable of sensing on the ground moisture or availability of water, like that. So that's why we are adopting them. We are trusting that their research is like confident and all. So NDMI can also be chosen for our study. Then another index is normalized soil moisture index. So soil moisture index is also, it's not directly giving soil moisture, it's an index, relative value. So here SWIR 1, that is band 11, and SWIR 1, 2, that is band 12 were chosen. So here you can see their large wavelength. They are short wave infrared in the electromagnetic spectrum. So they are available at 20-meter resolution. So that is why if I calculate NSMI, it will be at what resolution? 20 meter. NDVI, however, those bands were available at 10 meter. So if I calculate using the equation, I would have at 10 meter. So now you see some are at 10 meter, some are at 20 meter. So what we should do? We should bring them to same. Yeah, so that was resampling. So resampling has to be done so that everything is at one particular resolution, either 10 meter or bring everything into 30 meter as per our, or 20 meter as per our requirement. So once we had all these predictors ready, our predictant is the field soil moisture, which we have already taken with the help of the theta probe. Now I want to build a regression model. My regression model will be of this form. Soil moisture volumetric is equal to a constant or intercept plus these weighted combinations of all these band based indices. So here x1, x2, x3 should be what? No, x1, x2, x3. What is y here? Soil moisture. What should be observed? What are our predictors? Yeah, so what are the independent variables here? NDVI, NDMI and NSMI. So x1, x2, x3 are these things. B1, B2, B3 are their weights or coefficients. Okay, and B naught is an intercept. It may exist, it may not exist. We are putting it there, let it be there, like that. And some satellites like Sentinel also make available some kind of platform, like it is their toolbox. You can do the extraction, you can do the resampling, you can do the cloud correction inside that. Okay, so that is called Snap. So Sentinel's toolbox, Snap. So there are a number of YouTube videos available on how to work with Snap toolbox. If you are interested, you can go and visit them and study that process one step by step like that. So Snap allows us to extract, do the cloud correction, resample, do the algorithms like plus minus kind of things, and get whatever we want. Okay. And again, resampling was also done before this step that we have already discussed. Yes, that is our task. This is our model that we have proposed, right? Soil moisture is equal to, let this be our simplest model. Now we can always do things like machine learning and all, where we cannot write an equation, but we can write it as a function of all these things. Yes, yes, this is all going to come from the data of x1, x2, x3 and available SM, soil moisture, on the left hand side. So how to do that? We have multiple tools. Like I said, simple equation like this, or machine learning based models we can choose. Hmm. Huh. No, no, not like that. So Sentinel says that, okay, these bands I will cover with a pixel resolution of 10 meter. So they did that, they have made it available to us. Certain bands, we are not going to give it at 10 meter, we have only at 20 meter. So that is available at 20 meter only. Certain other bands are only available for 60. It is like that. They are giving it to us only at that resolution. Now we can do aggregation or disaggregation and make them 60 to 10 or 10 to 60. That is up to our desired work. It's fixed. If it is mentioned that okay, I am giving band of red only at 10 meter, then from original thing it's only 10 meter. But I can make 10 to 20 on my own, like if I do the resampling. But Sentinel is not responsible for the accuracy of that. Sentinel says, I will give you only this thing. Whatever you want to do, you can do the adjustments. Okay, like that. So here, now we can have this kind of equations, and we can use Microsoft Excel, or we can use some kind of programming language to get these coefficients, because this is fitting a linear regression equation. Or if you want to go for a non-linear relationship, you can use their appropriate toolboxes and commands to get that idea. So have you done linear regression fitting before? Yeah, so that is it is tedious. So you need to, like, if you have many data points, you have to put it in something like an Excel at least. Hand calculation becomes difficult, right? In Excel also there are many options like data solver, which can also be used to find out what are these unknown coefficients and intercepts, etc. They will also give us the accuracy, like what is the R square of that fit, or what is the mean error of that fit, or what type of interval you should put. All these things are now readily, like at our fingertips. We just have to learn how to do in Excel. We can get these numbers. Okay, so here we went for a very basic model. No machine learning, nothing. Very basic learning. We can actually see what are the coefficients which are more having weightage, which are having less weightage, like that. Okay. And one more thing we have to take care of, that is these NDVI, NDMI and all, they are having different maximum minimum limits. So it's better to normalize them to one single maximum minimum limit, like 0 to 1 or 0 to 100, so that it is like minimizing the chances of scattering of the values. So they are all in one sample set, like 0 to 100 or 0 to 1 or something like that. Okay. Now let us say we did all that. We did Excel, we got all the B1, B2, B3 and everything. We can plug in and get the answer. What is the use, what is the performance, we have to still verify, right? So therefore we have to do whatever sample data we have collected, we have to split it. Some for model development or calibration. That is around 2/3 of the available data, we earmark it for the development or calibration. Remaining 1/3 we can kept for validation. That means I am giving a new data set, can the model perform still better, like that. So in model development stage, we develop these B0, B1, B2, B3 like that. In model validation stage, we apply all these things in the right hand side and get the corresponding answer, whether the predicted SM and the observed SM are still correlated well or their error is very low, that we have to decide. So when we develop the model, we know that calibration means it is minimizing the error between the prediction and the observation. So that calibration will always therefore give you good R square, good like lower error, etc. But it should be maintained in validation. That performance should be maintained while we are doing validation. So that is where the check comes. If I give a fresh set of data, will this model stand or not? Okay. Now we move on to the actual work. Okay. So this particular watershed was lying in the mid Mahanadi river basin. So you can see that river Mahanadi is tributaries, main channel, etc. is there in the image. Okay. So if I extract NDVI after calculation, I will get this kind of imagery for NDVI, NDMI and NSMI. So you can see the values are ranging from -1 to +1 in this calculation. Okay. So some locations having minus values means no vegetation. In NDVI, it's water body. In NDMI, you can see that wherever moisture is there, it is corresponding to really dark colors. Then in NSMI, you can see the blue color is corresponding to the like blue, it's a color that I have given. The color scheme is all user defined, but there is a range of number which will refer to greenness or which will refer to water body in each of these cases. So these are our predictors. So for me, in this particular area, let us say I have taken some 300 measurements. Okay, total of many dates, many locations, let's say 300 are there. So maybe on a given day I have taken around 100. If 3 days let us assume, that means on a given day I have taken 100 readings from the plot or the watershed. So I go to that particular pixel where that data was taken, and if I pick NSMI value, it is one predictor for that particular point. I go to the same pixel in NDMI and pick the value, it is my X2. I go to NDVI and same pixel, it is my X1. And when I put the probe in that location, what value I got would be the corresponding soil moisture. So all the 3 dates, all the locations, they are all each data point now. So if I have 3 dates, 100 samples per day, then 100 into 3, approximately 300 would be my total data set. I can divide 2/3 calibration, 1/3 validation, like that. So that is how this process was carried out. Now they were all resampled to 20 meter. That's why we have all of them in 20 meter. Now, these are the variations across the space. So we have 4 dates. Okay, February of 2017 and November of 2016. So November of 2016, 2 dates were available without cloud cover. February of 2017, another 2 dates were there without cloud cover. So we were only able to get only those dates without any difficulty like cloud cover and all. Huh. No, we had actually like let's say this campaign was carried out definitely not during monsoon, post monsoon, but before the summer also, like around 6 months. But we have difficulties like sentinel should pass on the same day. And then we also have limitations like there should not be any significant cloud cover. So finally only 4 such dates were available in this particular case. But if you plan previously, like this was like somebody else's project and then we have utilized. But if it is our own project, we have control when to do the monitoring so that I will get maximum number of points. But here, because it is taking the already observed data and then using new satellite missions data, so that the overlapping dates were lesser in number. So we have 4 dates. Okay. And on these 4 dates, NDVI, NDMI, NSMI of so many locations were utilized. Okay. Around 83 locations. Yeah, around 83 locations were used in this particular field campaign. And we have been able to get only 4 dates multiplied by such 83 locations. So the area is of the area of the watershed. Here we are not concerned about how much area we have, but in that area 83 is a very good sampling because it is less than 500 kilometers square. We have resource limitations. Within 3 hours of something we have to cover the watershed. Then it cannot be in the farmer's field, we cannot go and put all the time. So some limitations are there. So in that way. So you can see 83 locations are being plotted in the x-axis. Okay, it's not time series, but it is the spatial record. 83 in each imagery you will see. So you can say that they are ranging in some value to value from the figures. Okay. So some of the data points will give some peak value. Some of them will give something like negative side. So these are coming from the indices. These are from, this is not soil moisture yet. This is what the index values are across the 83 locations from the image that we saw previously. The image that we saw previously was one day. Similarly, 3 extra days are there. From that they were picked. Okay. So this is giving us an idea of fluctuation across space. So do we see fluctuation in space? Yes. So in 500 kilometer square area, fluctuations are of this range. Okay. So that tells us that we need very well defined or high resolution soil moisture data to actually capture something useful. Otherwise, if somebody tells me, okay, 500 kilometers square, there are 3 pixels, these are the values. Now we understand, is it trustworthy? So much variation across 83 locations, right? So now NDVI, NDMI and SMI has to be clubbed to get our soil moisture. So let us say somebody did that work for us like Excel or programming or something like that, and we got the equation also. Okay, so I have put here one figure that summarizes the performance of the model. Okay, it shows scatter plot between the measured value, that means observed value, and the estimated value using the remote sensing equation, and what are the performances in terms of R square and RMSE. So we also have ways to express the performance in terms of mean square error, root mean square error, R square value, then some other like percentage bias, all those things we can use. We can also say that if I want to predict in future, or if I want to correct it in future, I can also generate an equation for this model, which is a best fitting equation, so that I can apply that equation to once again do the correction. Okay, so I am taking the equation y is equal to b naught plus b1 x plus b2, I get an SM. SM predicted, if it has to be equal to SM observed, some another correction. That could be from similar kind of uh, regression lines. Okay. Now, what we also see is that how much variation is there in these dates and what is the standard deviation across the locations. So, we want to analyze the variability in space. That is our end goal in this particular study, isn't it? So, we need to know that across space how variability is captured, right? And how the model is suggesting that thing. So, here on the 4 dates, November to December 2000, November to February 2017, the 4 dates, we can see that the average value, it is following a pattern. That means it was high in the post monsoon, immediately post monsoon it was higher, around 0.3 like that, and the value by the time it goes to February is hovering around the wilting point kind of range, isn't it? So that is suggesting that kind of variation, seasonal variation, immediately after the rain and after winter season. What is the average soil moisture? And with each of these values, you can see the pink bar suggesting the range of the standard deviations. So here you can see standard deviation is higher in the post monsoon. That means there is a very broad range of variation. Whereas by the time we reach the February or just pre-summer, what we see is that it's varying in a narrow range as well as in the lower side. So this kind of capturing patterns is also important. That means our satellite should be able to distinguish the seasonal variations also, because tomorrow I am going to rely on the satellite without any ground data. So I should have confidence on multiple things, not only the data but also the variability, deviation, or ability to capture across the year patterns. So ideally I should have multiple times of the year this kind of data, so that my model can be developed more robust, as a more robust one. Okay. Now the end application. So the end application is to get a continuous soil moisture map of the watershed. So if I use the 83 locations, I can still get one, isn't it? Which software we would like to use in case of developing these kinds of maps? GIS softwares, isn't it? Because they will allow us interpolation on space, smooth interpolation, or pixel wise you want to show, that is also possible. So if I have data from the Sentinel that has gone into the equation that has got me the predicted soil moisture. I check the performance, it is satisfactory because 80% is very good R square from satellite. So I trust the model to some extent. So now I applied that equation to all the pixels. Earlier we had only 83 pixels per day. Now on a particular day, I applied to all the pixels the same equation. Okay, so what will I get? The soil moisture value for all the pixel correspondingly. So this kind of continuous soil moisture mapping was possible by the model that we have generated. So if I want for another date where I don't have any field data, I will take the data from the Sentinel. Because it is my study area, I can use my equation. But for a different study area, should we recommend the same equation? No, we should do our own some case study kind of development of the model and then apply it. Now, in times of need, when there is no chance that we are going to conduct a model development exercise, we may still use such available equations. Because you will see in water resources, we use so many equations like left and right. We see that they were used in Deccan area, some were used in UP area, some were in America, but still we use it, right? So there is a small disclaimer there that it is all an estimate. Yes, this is observed data, but it works well for our study area. But tomorrow you want to apply for your study area, you can still use it, but only as an estimate. An estimate requiring validation, right? So that is where the additional effort should come. So this kind of work always has a merit because every area is a new one, isn't it? Every day soil moisture is dynamically changing. So no model can give 100% performance. So tomorrow I will again redevelop another model trying to see if my RMSE can be even lower, isn't it? But the work still has a merit because it's giving a more accurate value than previous day. So you will see in literature there are many study examples that focus on soil moisture estimation using XYZ satellites, XYZ indices, but they all have some merit because each one tries to perform well over the other, or it is over a different area or different season or different purpose entirely. Because the merit of this kind of application comes in precision agriculture also, IoT based irrigation. Because IoT means what? You are not going to include a person anymore. You are depending on sensors and all these kinds of automated things. So there also satellites can play a very good role. Just have the connection should be very accurately done, isn't it? So this is just a first step. There are many more steps where we can take, many more paths we can take to achieve different kinds of outputs from this kind of research problems. And it is not very complex because these days people are making everything in a readily usable form. Like somebody doesn't have to take a remote sensing course to operate a snap tool. They have to watch a few videos, read a few books. We can understand the necessary part of it. But if you go to microwave remote sensing, things get a little more complex because microwave remote sensing has algorithms in place which somebody has to define some constants and all. Then we have to apply that. So in that case, we have to have some additional support from coursework or extra reading like that. But optical is relatively easy. So people can adopt it for a larger goal without investing too much in the steps, different steps. So that summarizes the talk here. So if you have any questions, Anything, anything you want more clarity on? Non-linear can also be done. Then the equation format will change, but you may find that performance is not improving much. Yeah, if linear performs so much, non-linear may give you maybe 0.8 may become 0.83, like that r square. So if you find such things, then naturally the simplest way can be the, yeah, like that you can find. I mean, I'm not sure, but if you go for some machine learning, maybe it captures some more patterns and gives you a little more r square, like 0.87 or something. That is possible. So we have not explored nonlinear in this case. We are exploring machine learning based now, so that if any improved performance can be achieved. So right now we found that even if we remove one, we are going to get a reduction in performance. So we feel that three of them are good. And if tomorrow somebody brings in a new index and tells that that is also a good indicator, we should incorporate that and check whether performance substantially improves. So in our different combinations we tried, like we didn't use NDVI and use the other two, or we used the first two and disregarded the last one. But it didn't improve our performance, and rather it decreased. So we found that, okay, optimally let them be there, all three of them, and then we proceeded. Mm. Mm. Yeah, we are definitely getting less error. Improvement is there. The only thing is it is complex now. If I want to explain to somebody how the model is, I just have a black box that you put it into, yeah. Yeah, we have to, no, we don't get. So how will a third person use it? That is the question mark. Yeah, I mean, it will give me a paper, or it will give me a like, yeah, but I don't have any practical use for the community. Like you must have heard of pedo transfer functions, isn't it? For calculating. That is also there. That is also possible. So people wait for the best one to come. Yeah. But you will not guarantee that to the third user. He cannot repeat correct 10 times and get the same value. So some things are there, but the model is there. Like it's like a computer program. You give the data, it will run and give you the result. But we cannot put it in words anywhere or equation anywhere that directly somebody can relate. Okay, this is having high weightage, this is having low weightage, like that. But definitely it improves, because it captures all the non-linear connections and everything. It definitely improved the performance. And nowadays deep learning also is there. That will also give a little more better results. Hmm. Yes, yes. The more the data, the better for machine learning tools. Yes. Like in this one, we had only 332. Still, we can use machine learning, sorry. 332 sample data. So I am not showing here calibration validation. I have put all the data in one plot just to give an idea. If I do the calibration validation, it would be like around 232 for calibration, remaining for validation, like that. So it would suggest that maybe calibration time it was 0.80, validation time it was around 0.7 something like that. So when I put all the data, R square came up to be around 0.79. So like that. Uh, optical means surrounding that visible light bandwidth. Microwave, so you can see that so in our bands that we used, you have seen very visible infrared, near infrared. So all of them are like nearby that visible range. Okay, like 700 to maximum 1200, like that nanometer. But you move further, there are these kinds of waves that can also be captured by corresponding sensors. So sensor would now have to be a different sensor, like that can read the microwave signal strength and all. So those sensors are actually more reliable for soil moisture. That's what research says. Ease of use is a different thing. High resolution availability is also a different thing. Microwave sensors may not offer meter scale. They may have a little more coarser thing. But they are more accurate and less affected by clouds. So that way also they are good. So they are better for getting soil moisture. They are less prone to cloud related errors. But the problem is in the resolution. I cannot get 10 meter, 20 meter of that easily. So that is where we make a decision that okay, I don't want microwave, I'll go for optical. But there are many choices. Many studies have conducted on microwave remote sensing. So it requires a little more, technical background, because they have a little more complex equations and algorithms to follow. So that is there. Mm. Yeah, they have more, because it may be less what you call uh, less complex machinery or instrumentation for that related to compared to microwave, like that. Okay. Thank you all for your patience.
And it's very like simple and very